So our first lecture is titled, How Do We Know? Which is, of course, a big question. And we're going to dive down here into different ways of knowing. So this is, of course, a science class. And so we're going to be looking at how science differs from other ways of knowing. And so this big question of what is science and how is it different from other approaches we take to understand the world. And as part of this, we're going to be looking at the questions or hypotheses that science can answer, and also talk about questions that can't be answered by science. We'll also look at the assumptions that scientists make and contrast scientific ways of knowing with other ways of knowing, right? Such as personal opinions or beliefs. So we need to start off by thinking about the fact that there's lots of different ways of our understanding the world around us. So what is the approach that science takes? So there's several attributes to a scientific approach. One is that it's very data-driven. Right? So it's driven by evidence, driven by observation. Sometimes we can do experiments, right, to test hypotheses, to test questions. And for some types of variables, we can also quantify them, right, and develop mathematical models to kind of predict what will happen, right? So if we think of a field like astronomy, for example, they can't do experiments, but they can do a lot of observation and they can develop these quantitative models about the universe. And we use this to understand the natural world. So again, evidence is very important. We're quantifying things. And you'll see in here that I also talk about methods, that the methods that a scientist use are reported. And the reason for this is because anything you do in science should be reproducible, right? So if I go out and I measure the stars, for example, and I publish a paper on it, right, I put all of those methods in there so that the next astronomer can go and try to do those exact same methods, and they should get the exact same results. So this is very important. And if you've ever read a scientific paper, why the methods are so long and convoluted is because it should be reproducible, right? It should not be dependent on who is doing the measuring, right, or who is doing the reporting. The idea is that we're figuring out things about the natural world, and if anyone did the exact same thing, they should get similar results. So what are our assumptions? One assumption is that we can actually understand how the natural world works, right? And it's kind of incredible when you think about what science has brought us, right? So right now we're in the process of getting a vaccine, right? We can fly in airplanes through the air, right? So it's really fascinating when we think about how this process has allowed us to understand these basic laws of physics and chemistry and biology. That said, you can only answer a subset of questions. So it's not as if we can use science to answer every question that's out there in the world, right? And partly because we have to be able to test our questions. We have to be able to gather evidence. We have to be able to come up with a way of discerning whether we have a strong hypothesis or a weak hypothesis. So it's important to realize that even though scientific knowledge is very strong and incredible, right? I can get on a plane and fly to the other side of the country. It's different from what a philosopher would call, big T truth, right? Absolute truth, right? So we can do a heck of a lot through science. We can make vaccines that work. We can do all sorts of incredible things. But there is a difference between scientific knowledge and this kind of more philosophical idea of truth. The other thing that's important is because this is such an evidence-based process, data and evidence is changing all of the time, right? As people do new experiments, as people publish new studies. And so because of that, the nature of scientific knowledge will change over time. And as new evidence accumulates, scientific opinions will shift on something in response to that change in evidence. Now, it's important to realize that there are other ways of knowing, right? So if we think about things like beautiful art, or we think about religion, or we think about philosophy, there's lots of other ways in which we can approach the world and try to understand the world. So science is one way. And in contrast to some of these, science just excludes supernatural explanations. So we're really focused here on trying to explain the natural world, and that's what we use when we develop hypotheses, right, about why the stars look like they're in different places at night, right? We would come up with a natural explanation with regards to the planets moving and all of that, right, to try to explain that. Again, science should be reproducible, right? So it's not subject to an individual scientist's personal desires or beliefs, right? They do these certain methods, they get the evidence back, and they report it. Science should also be what we call valid, and that means that the evidence you're collecting, the data you're collecting, should be pertinent to the question you're trying to ask, the hypothesis you're trying to test. So that brings us to, what are our testable questions? What are our testable hypotheses? So I've already said we're going to be talking about the natural world. So objects, organisms, particles in the natural world, they have to be able to be observed. So we have to be able to observe them. In ideal situations, we can perform experiments, but again, astronomy is a great example where, you can't really move around where our planet is, right? So experimentation is not required in science, but it can help when we can do it, when we can, expose a mouse to a certain chemical and then have a control of mice that aren't exposed. That can really help us discern, in that case, the health impacts of a chemical. So again, observation and experiment. I'm repeating myself here, not based on individual preferences, aesthetics, beliefs. So, for example, say we were interested in genetically modified food and we were trying to figure out if there was a health impact of that. Now, mice are a model organism that are used in the sciences to test these types of things. And so that's a testable question. So we could take mice, we could feed some mice GMO food, we could use control mice to do non-GMO food, everything else is the same, and we could measure different health outcomes on those mice. So what might be an untestable question? Believe it or not, whether or not pineapple is delicious on pizza or sausage is better on pizza, that's an untestable question. Now, we can quantify certain things. We could quantify how many people prefer pineapple on pizza versus not. But we can't really say that there is a true answer to whether pineapple is better on pizza or not, or whether blue is a more beautiful color than red. So here we get into, again, these ideas of aesthetics, etc., and they're value laden, right? Like I really like pineapple and you may not. So one way to think about science is to contrast it with solving a mystery, right? So you can see this table where we have how scientists approach a question, and then on the right we have how detectives approach, let's say we have a grisly murder that we have to figure out, right? So again, this very evidence-based process. So a scientist is going to ask questions to get new information about some natural phenomenon. Detective is going to go out, interview people, try to figure out what happened, gather evidence. You make observations, right? You propose different hypotheses, right? So a detective is like, oh, maybe it was the butler, right? Or maybe it was, so these are your different hypotheses, different scenarios. You collect evidence, you construct explanations, you critique and evaluate, and you discuss with others what that evidence suggests, right? And then you communicate your final hypothesis. So a scientific argument has these different stages where you have a claim, and then you have evidence to support it, and then you have a rationale, which is kind of the reasoning that explains how all that evidence fits together, and actually this ties back into this idea of validity, right? That evidence fits back into that claim and supports it or refutes it. Now, as part of this, we have to realize that scientists are human, right? Believe it or not. So this is a social endeavor. So how do we come up with this process that is very reproducible, which is evidence-based, and deal with the fact that, okay, scientists are human too. They're going to want status and prestige, all the kind of, human foibles that anyone else has. So one piece that the scientific community uses to kind of weed these kind of bad actors out, is through what's called peer review. And this is not just the sciences, right? Other disciplines also have this peer review process through which results are communicated to others in the field. And so you can see here, say I'm doing an experiment on GMO and non-GMO food, to stick with that one, right? So I use my scientific method, I have my mice, I have my hypothesis, predictions, I test all my mice, right? And then what do? I write up that paper, right? So I write up a paper, it has all the methods in there, and then I send it out to other people who are experts, right? Who are experts and know which are the good health measurements to measure on the mice, who know, the other literature on GMO impacts, all of that. Those people review the paper, right? And then it may be accepted for publication or it may be rejected for publication, right? And then once, say, it does get accepted, then you have publication, and then you have other people out in the scientific community who can review it and give further feedback. So there's this looping of the process, right? And having that stage where you have other people with scientific expertise look at it, right, helps to keep some if we say bad actors or weaker hypotheses or weaker methods, for example, from getting published, right? That's not to say that that doesn't happen, right? It's just to say that this is another layer at which we can kind of try to create an amount of scientific literature that has validity. So we're actually going to be out here gathering evidence to test some question. Now, a lot of times what we want to know is a cause and an effect, right? So maybe we're interested in, if I smoke, am I going to get lung cancer? So does smoking cause lung cancer? Now, this is a testable question, but it can be very difficult to prove, in part because in the case of smoking and lung cancer, our natural body is very, very complicated, right? And we have a time lag, right, between years of smoking and when your cells might develop cancer, all of that. So what kind of evidence could we gather to test this question? Well, we could look at people who smoke and people who don't smoke, and we could try to pair them on every other thing in their life is similar, right? Except we have smoking and non-smoking, right? And then we could look at the rates of lung cancer in those two groups. Now, we can't, of course, do experiments, right? We can't assign random people into smoke-filled rooms and others not into smoke-filled rooms in a controlled way, but we can do that with mice and rats, right? And so we can expose, test animals to either the chemicals in cigarettes or the smokes, right? And we can monitor those in a control over time. So And now experiments, as it says here, provide the strongest evidence, but I've used this example on purpose, right? It's obviously we have ethical constraints that keep us from performing certain types of experiments, even for questions we really want to know about, right? About, lung cancer in people, because we couldn't, it wouldn't be ethical to do that particular experiment. And so we have to couple experiments with other animals with more correlative data from people. Now again, regardless of who is doing a given scientific experiment, collecting the evidence, they should come up with the same conclusions, right? Regardless, so it's independent of who is doing the science. And this is partly why it is so important to have that detail in the methods reported for any given published scientific work, because someone else should be able to repeat it and get similar results. Of course, once you have your results, once you have your evidence, right, we can think back to the detective analogy, right? Different detectives might see the same evidence and come up with a little bit different opinions as to which claim it supports. And the same is true in science, right? So you get your results, right? And then the discussion of those results and how well they fit the hypothesis or the claim is to some extent more subjective, and that's where scientific debate and peer review and all of those things come into play. Now, a scientific opinion is therefore very narrow because it's this based on this kind of evidence-based process. If we think about just opinion writ large, right? Like I have an opinion, which is I actually love pineapple on my pizza. So my opinion is pineapple is awesome on pizza. So very controversial opinion. And that's, of course, broader, right? That's not a scientific opinion, as we've already talked about. It doesn't have evidence to support it, right? It's just based on I like it. I think it's delicious and I'm sticking to it. So how, given that people are social animals, how do we come up with a process that actually allows us to accumulate data over time, accumulate valid evidence over time? So some of this is a social norm within the scientific community, right? And so I've put here, there is no greater sin than falsifying data, right? Which is probably not true, like, murdering someone is worse, right? But the point is that the social norm is you do not produce false data, right? So that's the thing that will get you kicked out of the scientific community and kind of shunned, right? Because what would be more confusing in the world? How are we going to figure out how the natural world works if people are just making up numbers, right? So again, very a strong norm against falsifying data because, of course, evidence, data, methods, all of that are the key to actually figuring out how the world works. The other thing is reproducibility. So if I see somebody's published study and I'm like, those results look so weird to me, right? Well, then I can go and I can do the exact same study and see if I get the same results or not. So this idea of replication, of having multiple studies and reproducibility is also really important in the sciences. Peer review is important, right? Because it allows people who have that expertise in a given area to look at your methods, right? To look at them in the context of all of the relevant literature, right? And provide feedback. So review by experts. And also skepticism, right? So I just gave an example where I'm like, those results look funny to me, right? So is particularly when a hypothesis is brand new, right? And we don't have a lot of evidence yet. There's not a lot published on it, right? It's going to take a while for scientists to actually think there's support for that hypothesis, right? Because it takes a while for evidence and data to accumulate. Now, you do have this process of what's called science denial, right? And that can happen sometimes within the scientific community, but also prominently outside of the scientific community, right? When sometimes people who are very invested in other non-scientific ways of knowing, right, refuse to accept scientific ideas, despite the fact that they're supported by a preponderance of evidence. And in this class in environmental biology, of course, climate change is a big example of that when we think about climate denial. And of course, there are all of the politics behind that as well as to why it would serve some people's purpose to deny the science. So I've been talking about hypotheses, but I haven't defined them. So I want to define what a scientific hypothesis is and then contrast it with a scientific theory. And that's really important in part because when we start to think about all of this crazy politics, right, it's important to realize that a scientific theory is very different from how we use the word theory out in the, kind of colloquially or out in just everyday life. So first off, our hypothesis, again, has to be natural. So a natural explanation of how the world works, right? Used to explain some pattern, some set of observations. A theory is kind of the next step. So say you have a hypothesis and you test it and you do things with mice and you collect data and other people do it in their labs as well. And the data continues to support that hypothesis. So your hypothesis has become well tested, lots of papers published out there. People in the scientific community widely accept this, right? Then it kind of grows up, if you will, to become a scientific theory, right? So these are our well-tested, well-accepted hypotheses. Gravity would be an example, right? Okay, this is, gravitational theory. It has obviously been well tested and is now well accepted. Heliocentric theory, right, is that the Earth goes around the sun, right? Used to be controversial back in the 16th century, right? Now it's just, we actually accept that as a fact, right? Evolution would be another scientific theory with, again, well tested, widely accepted. So scientific theories are supported by large amounts of evidence, have been repeatedly tested, and are accepted by, kind of consensus views within the science. So again, theories have more evidence to support them than hypotheses. Now, this can be used when we think about debates, right? The fact that scientific theory means something different than when someone says, oh, I've got a theory about that, right? Because when they're saying that, oh, I've got a theory about that, right? They mean just some, a kind of a wild guess, right? So unfortunately, in the debate spectrum, this fact that people don't understand this distinction of how scientists use the word theory can be used to kind of create the impression that certain scientific theories are weaker than they really are. So science is obviously an iterative process, right? You come up with hypotheses, you test those hypotheses. Over time, they may be refuted and rejected, or they may get developed into whole scientific theories. As evidence accumulates to support them, a hypothesis, again, could become a theory, right? If the evidence continues to support it, and if the evidence continues to support it over long periods of time, right, then we just accept that as a fact. Right? And so heliocentric theory would be one of those, right? We don't go around debating whether the Earth goes around the sun anymore, right? That's relicked back to the 16th century. We just accept that now as a fact. Now, it's important to realize we think about things like climate change and science denial associated with them. But this is not a new phenomenon, right? We have had science denial in the past, right? It's because sometimes certain scientific theories really butt up against other ways of knowing in a way that creates conflict. So let's look at heliocentric theory, right? Back in 1543, Copernicus publishes his work, right? And it was... as you can see, there was a lot of denial within the Catholic Church, so issues a decree to alter it, tells Galileo not to publish it, right? Galileo gets convicted of heresy, right, and gets arrested. And it wasn't until 1835, right, that the Catholic Church lifted the ban on Copernicus's book. So scientific hypotheses and theories can be very controversial, and this is, again, not a new phenomenon. What is a new phenomenon are things like Twitter and Facebook and Instagram, and I don't know, I'm sure I could come up with some others if I if I spent time talking, right? And so that's my dog, so we're kind of awash with all of these memes and images, and so because of that, right, it can be hard for us to know, well, is this science or is this not, right? Are we talking about people trying to get us to believe certain things, right? And so I have good old Abe here talking about how you can't believe everything on the internet. And then the other two, since we've talked about smoking and lung cancer, I put some ads here from the when would this be? Maybe the 1950s for cigarettes. The one ad claiming scientific evidence that, smoking is somehow good for you, right? And so how do we, particularly if this isn't your field of study, if you're not a scientist by training, how do we, given that we're awash in all of these images, people who want us to do different things, buy their cigarettes or, vote for them or whatever it might be, how do we figure out what really the science supports? Okay, so this is my favorite meme, right? So just talking about memes. So this is my favorite meme, which is the Credible Hulk, right? And it says how the Credible Hulk always cites his sources, right? So again, when we think about science, right? So say we're going to stick with climate change, right? And you're talking about the earth being warmer or the sea levels rising, all of these different things that we're seeing. It would be important to cite your sources. Are you getting that from the IPCC? Are you getting that from the National Academy of Sciences, right? Because that allows people to go back and look at those sources and evaluate whether those are legitimate scientific sources or not. So one way we can kind of make our way through this wilderness, if you will, that we're presented in social media and ads and TV and all of that, is to look for those individuals, right, and their sources, and then to look back to the sources. So I'm just going to tell you some credible sources for scientific information, and you likely can access them in your pocket, right, because of the wonderful thing called the internet. So here are some. By no means is this an exhausted list, right? In the U.S., we have what's called the National Academy of Sciences, and good old Abe made the National Academy of Sciences back in the day, right? And the National Academy of Sciences is charged, their mission is to provide independent, objective advice to the nation on matters relating to science and technology. How smart was Lincoln to think of that, right? That we need this body that's independent of all of the political madness, right? That we can say, okay, you are charged with providing independent, objective advice, right? So we can go, when we talk about climate change, we can read reports from the National Academy of Sciences on that. Right. Other credible sources I have here is NASA. We'll look at the NASA website as one of our reading assignments, NOAA, and then, of course, many others that we think about, the National Geographic or the American Association of Scientists or Science Daily, right? Lots of different ways that we can access good scientific information. So say we were interested in, say, this is looking at health effects of cannabis, right? So we know that cannabis is getting legalized now and is legal in many states, right? In some states just for medical use, for some states for recreational use, right? And you might want to know, well, what is the data? What do scientists think about how that impacts health? This is actually a report, a 2017 report from the National Academy of Sciences that looks at that, right? And you can see all of these different chapters. I've only put 2 chapters and some of the bullets associated with them, right? In terms of, and you can see there's kind of good and bad health effects, right? So we have these therapeutic effects, right? So let's go down to, moderate evidence that cannabis is effective for improving short-term sleep outcomes, right? If you have trouble, if you have sleep apnea, things like that. And here over here in chapter 7, respiratory disease, substantial evidence. So substantial evidence of a correlation, right, between smoking and worse respiratory symptoms, including chronic bronchitis. Right, so again, great source of information, National Academy of Sciences publications and reports. Now, of course, even some of these, particularly if we think about our government agencies, right, they can be subject to political pressures, right, and they can have their directors. Their directors are politically appointed, and so because of that, that can put pressure on these agencies to not present some of the science in a non-political way, right? And so we saw this in the Trump administration, right, with the federal EPA website changing its language, right, with regards to climate change, with regards to the Clean Air Act. And people were actually, doing screenshots, right, to try to document what was changing on that site under a new political appointee. So I think it's important to just be aware of that process. So given that, how we're going to, again, make our way through this wilderness. So one thing is, if you're not a scientist yourself, your friends can still be scientists, right? So befriend a scientist, right? So I think that most scientists are friendly. They may not be extroverted, but they're friendly, right? And they're happy to have a conversation with you about their work or about science in general. If you're on some kind of social media like Twitter, you can follow a bunch of scientists, right? Or follow scientific organizations. And based on that, you can develop your own perspective, your own approach. And one thing I would recommend is just anytime you have a source of information, right? Say it's a photo or a meme that you see, or say it's something that looks much more scientific in terms of its format, right? Actually develop some skepticism, right? So is it a scientific source or not, right? And if you say you have a report, where are the citations at the end, right? So do they have links to their sources so that you get more detailed information? What are the credentials of the folks who are producing any given science, right? So obviously, if we were going to talk about climate change, we would want to look for people who, had that training and expertise to understand how the Earth's climate worked. And then, of course, we have social media access, right? So lots of scientists are on Twitter. They don't have as many followers as celebrities, right? But we could change that, right? So scientists are excited about their work, and you can follow them, you can befriend them, etc. So there is also a difference between scientific argument, right, which could, again, we talked about how you get a certain set of results, but different scientists may interpret those results differently, right? And so there may be an argument amongst scientists about whether certain results support a given scientific hypothesis or not. And that's a scientific argument. And that's different right, than what we would call a general debate, right? And this gets back into this idea of science versus opinion, right? And the broader idea of opinion. Like, so I can debate you about pineapple, right? But that's not a scientific argument, right? So a scientific argument is evidence-based disagreement and talking about this kind of peer-reviewed science. Now, of course, in debates are kind of designed in some ways to shift your opinion. That's part of what a good debater tries to do, is get people to support their opinion, right? And so there's tactics that are used that aren't used in a scientific argument, right? So some of this is just like calling names, right? So criticize the person, right? Or another tactic would be to find one little bit, or, oh, you made a mistake there, therefore I'm going to refute the whole thing, right? So we see this in the IPCC climate change reports, right? People will find one little, oh, this glacier actually got bigger, right, out of the thousands of glaciers, right? And you said it got smaller, right? So you find one little piece where someone's made a mistake, right? And then you conclude like the whole big thing is a mistake. Right. And the other thing is, a lot of times in debate, there's a lot of aggression, right? There's a lot of conflict, and it's presented as a very simple thing. It's a yes or no, or a with us or not without us, right? And so that lack of nuance. And the one thing I have here is that, trust me, natural systems are incredibly complicated, right? And so that kind of tends to go away when we get into these realms of debating. And then, of course, there's also redirecting, right? So redirecting, and this gets back to, you want the evidence to have relevance, have validity when it is associated with the claim. So in a debate, right, you can have stronger versus weaker evidence, right? And so I did put this pyramid in here because it talks about the strongest evidence, right, would be if you do refutation, right? If you find a mistake, explain why it's a mistake, provide all your sources, etc. As opposed to down here where you're just basically, calling names. Okay, as suggested in this very lecture, I have provided sources. So some of this information about how we do science, how science differs from other ways of knowing, I got from a couple of publications. And so I want to cite them here if you're interested in finding out more.